let's go back for a minute or so to cubic functions. You are looking at the graph of a function f of x defined as x cubed minus 3x squared minus x plus 3. I can also write this function as y equals 2 x plus 1 x minus 1 x minus 3, because the x cuts are given and the coefficient of x cubed is 1. So this is the given cubic function. Now remember, from this function, as you analyze the applications of cubic functions, you can be asked to determine the minimum, maximum. You can also be asked to determine the gradient of a tangent at any point on the curve. So you can be asked to find the gradient of a tangent at a point P. You can be asked to find a derivative of my function at that specific value of x. But you must also remember, and we spoke about it on the beginning of a section, that the gradient of a tangent or the derivative at specific point on the curve is also called an instantaneous rate of change. So change in y over change in x, but at the instant, it's called the gradient of a tangent, a derivative, an instantaneous rate of change. Now, why am I going back to the rate of change? It's because the rate of change in the calculus section has greater applications, and not only the applications to a sketch. So let's look at further applications of rate of change. So what we are looking at now, we have a function f of x or a function y defined as x minus 3, x minus 1 and x plus 1. But I can have further applications of calculus, which you did in a previous section, and instead of saying that I'm looking at the function f of x as a cubic function, I can say that I'm looking at the function v with respect to x, where in this example my v can represent a volume of a box. So now I'm looking at a box with the dimensions x minus 3, x minus 1, x plus 2. It's not to scale, it's just a box with the dimension. Therefore, the volume of this box will also be x minus 3, x minus 1, x plus 1. The volume of this box is also a function of x. Now, you did the maximizing and minimizing the volume, the surface area, the distances between the functions. So we went from purely mathematical analysis of calculus and the cubic function on the Cartesian plane to some word examples where we had two-dimensional or three-dimensional concepts that we had to use calculus to solve. Now we need to move one step further and look at a real-life example. Let's say this box now, it's not just any box, it's a swimming pool. And in the swimming pool, I have a water. And I would like to know, if I'm pumping the water into the swimming pool, I want to know at which rate the amount of water will be changing. At which rate the amount of water is changing. What is my question about? Right, let's think again what we said just now. If I'm asked to calculate the gradient of a tangent to the given curve at any point, I can do it by finding a derivative of this function at the given point. If I'm asked to find the volume and then to maximize it, I will look for derivative of the volume. Now, derivative or gradient of a tangent is exactly the same as the rate of change. So instead of looking for maximum volume, I can also look at which rate the volume is changing, or at what rate is changing if x is the given value. So that's our first real-life application of rates of change, to looking at the derivative of a function, but in more real-life context. In your textbook, in exercise 9.5, you've got a few word problems that need our knowledge of calculus in order to find the solution. Now, in the question number 1, they are talking about a volume of water in a tank. So instead of talking about the volume of water in a swimming pool, they're now referring to a volume of water in a tank. And they say that the volume of the water in that tank can be described by the equation V equals to 5 plus 10t minus t squared, where t is a time in minutes and V is the volume in cubic meters. Now, to make it more of a real-life example, instead of asking you determine the derivative of V in respect to the given variable t, they say calculate the rate at which the volume of water is changing. Okay, because if I say to you determine derivative of V in terms of a given variable, it will be very mathematical. It more refers to a curve, it more refers to the graph. Here they say calculate the rate at which the volume is increasing. But that's exactly the same. The rate at which the volume of water is changing is the same as change of volume with respect to given time, dV dt. Okay, the rate at which the volume is changing with respect to time. So let's see what our derivative is here. Derivative of 5, 0, 10t, derivative, 10, derivative of minus t squared minus 2t. What does this statement represent? It represents the rate of change of volume with respect to given time, and it says that at any given time, the volume in a tank is changing by 10 minus 2t for every cubic meter per minute. They want it at the specific point in time at t equals to 2 minutes, so it's the same as finding the gradient at the specific point in time. So we need to substitute t as 2. So I get 10 minus 4 and I get 6. The rate at which the volume is changing in a given time is 6. 6 of what? Okay, it's nice to add the unit. Please just be careful about it. I said it's nice, it's not required. But how will the rate change? It will be 6 meters cube per every minute. Not very much of what you would use in science, but in maths it will be good enough. The most important is that number, the rate at which the volume is changing. In this case, it's increasing at t equals to 2 minutes. That rate is 6. So the volume of water with respect to given time, you see in a question it wasn't V of t, it was just V. You don't have to change notation. Was defined as 5 plus 10t minus t squared. So if I want to find the maximum of this function, I need to find the derivative. So it's either v dash of t or dv dt. Okay, so what's the derivative? We already had derivative. We said derivative was 10 minus 2t, and in order to maximize it, my derivative must be equal to 0. So I've got minus 2t equals to minus 10 and t is 5 minutes, which means that after 5 minutes, the water will start decreasing. So it's increasing for 5 minutes, and then after 5 minutes, it will start decreasing. Our last question, question C, was how long does it take for the tank to be empty? Now, what does it mean for the tank to be empty? Well, it means that the volume of the tank must be equal to 0. Okay, don't you feel like you're back at school with the bell ringing? It is 2 o'clock. So volume must be equal to 0. So we've got 5 plus 10t minus t squared must be equal to 0, or t squared minus 10t minus 5 is equal to 0, and we need to solve for t. How do we solve this equation for t? Well, we can use quadratic formula. So we have t equals to minus b plus minus square root of b squared minus 4ac, with c being minus, it changes the sign, over 2a. And we get 2 answers for t. Take your calculators out, complete the calculations, please. I hope that you completed your calculations and your answers. Let's say we round it up to 1 decimal place. We got 10.5 minutes. Again, unit not required, or we get minus 0.5. Now you see, I cannot really write a minute here since time cannot be negative, and therefore I have only one answer for t. So after 10.5 minutes, the tank will be empty. Please look at in your textbooks, please check it on the page 234. I would like you to go over the example number 2 and then look at the exercise 9.5. We have done question number 1, and I would like you to look at question number 3. A simple application of calculus in word problems when we are dealing with the rate at which something is changing. Please do the 2 examples now. Example 2 and exercise number 3.